Hey there. We're going to do one more example from section 5.3. This one's got a cubic polynomial in it. I want to compute a definite integral with the limit of a Riemann sum. So I haven't done anything. The book has something written about it, but I haven't done one of these videos where we have a cubic term. So we're going to have to cube things, and we're going to have to use that formula for the sum of the first n cubes from Appendix E. All right, I've given us an example here where there's going to be quite a little bit of algebraic manipulation to write this out. But I hope you are convinced that it's really not any more complex than the other things we're doing. We just have to be more careful. The more algebraic operations there are in a computation, the more chances there are to make an error. So I'm going to try to just sort of work methodically with you and calculate this thing once and only once, making it careful, but trying not to make the video too long. Okay, so once again, first thing you do when you're calculating a definite integral by limits of Riemann sums is you write down what your step size is, your delta x. Your delta x is always the width of the interval. In this case, its interval is width is 1 divided by the variable number of rectangles. Okay, so 1 over n in our example. Each one of these rectangles is width 1 over n. Then you write down your right endpoints. Your right endpoints are always your leftmost endpoint, lower limit of integration, plus I times that step size. So in this particular case, we end up getting something like 1 plus I over n. Okay, that's valid for I equals 0 to n, but I'm going to write down 1 because those are the endpoints I'm actually going to use in my Riemann sum. So that's step 1 and 2, always in calculating these things. Get your step size written down, get the formula for the right endpoints written down, simplify it. Because now we have to take that thing and plug it into that function. I'm going to give it a name so I can be consistent in my notation. That function, the sum of these squares and cubes and so on, let's call it f of x. So in our Riemann sum, the integral, which I'm just going to be a little bit lazy here and denote by I, so I don't have to write it again, and I give myself some more room to calculate. That integral, by definition, try to be careful and patient here with my notation, it's the limit of the Riemann sum. The Riemann sum, if we use right endpoints, looks like f of xi, I goes from 1 to n, times our delta x. Okay, and we exactly have the information that we need to plug into that. We have our xi right there. That's what's going in for these placeholders in f. Quite a bit of algebra to do. We've got our delta x. It's 1 over n. Let's get to it. So we've got the limit as n goes to infinity. So I goes from 1 to n. You can watch this video, speed it up so that you can watch it faster than when I can write these things. But I temporarily, for a second, everywhere I see an x, I have to put a 1 plus I. 1 plus I over n, pardon me. So I have to cube that. I have to square that. I have to take it to its first power. And then I have to add 1. That's my f of xi, and all of that has to get multiplied by delta x, 1 over n. All right, so now I've given myself quite a little bit of algebra to do. I have to cube out that thing, square out that thing using the binomial formulas. It's going to be hard to keep it all on one line, but let me try it here. I might have to shrink my handwriting size a little bit. So pessimistically starting as far over as I can, I'm going to write that this is the limit. Notice that I'm worried about room, but I'm not just dropping things from my notation. It's really important. You know, as I read students' work, sometimes I just see that some people are there kind of battling themselves in that they won't organize the notation on the page. So that's making the mathematics much more complicated. There's a really large amount of information here on the page, right? And it's hard to write it out. I'm stalling right now so I can rest my right hand. I'm stretching it so I can get ready to write the enormous amount of things I have to do. But what I'm going to start with here is I'm cubing something. I don't want to make this video too long, but there's a formula for expanding cubes, just like there is for expanding squares. So that's all I'm referring to when I write this formula. So I'm expanding 1 plus I over n cubed, and I'm going to write that it's equal to 1 plus 3i over n plus 3i squared over n squared plus I cubed over n cubed. Okay, that's how that thing would expand out. Likewise, 1 plus I over n squared expands out to 1 plus 2i over n plus I squared over n squared. All right, and then not really anything to do here, plus 1 plus I over n plus 1. All of that has to get multiplied by 1 over n. All right, let's gather some like terms. It looks like we succeeded in having enough room on one line. So let me expand out a little bit in my notation, get my sum and my limit written down. How many things had an I cubed in them? I only see this one. Of all those terms up there, I only saw one with I cubed in it, and it happened to be I cubed over n cubed. But how about I squareds? I'm going to help myself out and underline them when I see them. I got one right there, and I've got one right there. So 3i squared over n squared plus another one, that's 4i squared over n squared. All right, can you help me keep going here? How about, what else we got? Linear terms. There's 3i over n, two more right there, that's 5 so far, plus another one, that's 6i over n. Speed the video up if I'm going too slow for you, or stop it and do all this on your own. Now we got the constant terms. How many ones? Oh, we got one right there, another one makes 2, another one makes 2, there's one that's 4. So if I've done my math right, I've got that that's all multiplied by, or sorry, that sum is what I need to multiply by 1 over n. All right. Okay, so now I need to distribute that 1 over n through there. So a lot of this, I know it doesn't make the most exciting video in the world, but here I go, I cubed. If you do a few of these things, you can certainly organize and sort of write a little bit less than I am. I'm trying to write a lot here just in case it's not clear what's going on. I'm trying to leave a kind of breadcrumb trail that everybody can use. Yeah, but like that step I just did and the one I'm about to do, they can often be done together. In fact, I am going to combine, usually in my other videos right here, I would write some of this plus some of that plus some of that plus some of that. And then in the next step, I would factor out any of this stuff that doesn't depend on I. Yeah, out of every one of those things. I'm going to do those things at the same time. Okay, maybe it'll make it a more exciting video here. Maybe your adrenaline is pumping a little bit here. I'm doing 2 steps at once. So 1 over n to the 4th is a constant with respect to I, and it would be times the sum as I goes from 1 to n of the cubes. Same thing with the 4 over n cubed. Sum as I goes from 1 to n of I squared. 6 over n squared is a constant with respect to the index. 4 over n is a constant with respect to the index. Okay. So what do we got to do now? We got to use those formulas from Appendix E. Yeah, each one of these expressions we have a closed form for. We don't have one for I to the 4th, so we couldn't do a polynomial bigger than this. Thank goodness, this feels like enough work to me. But I'm referring to Appendix E in those formulas back there in my next line. Okay, so let me try to write a little bit neater. My handwriting's getting messy towards the end here. But this bracketed expression, the sum of the cubes back there in Appendix E, it is written, I hope you did that homework problem. It's a very interesting argument that those cubes add up to that quantity. Okay, and then 4 over n cubed, the sum of the squares, that's our n times n plus 1 times 2n plus 1 over 6. Hopefully this is all going to fit. 6 over n squared, the sum of the first powers is n times n plus 1 over 2. And then finally, the 1 added up to itself n times gives n. Okay, so now when we take this limit We're just going to, again, strategically look at each one of these terms. Look, this one, can you see it? Its degree is 4 in the numerator, because you have an n times an n, that's n squared, but you're squaring that. Its degree is 4, and the leading coefficient of the numerator is a 1. When you multiply all of that out, it would start off 1 times n to the 4th plus a bunch of stuff I don't care about. In the bottom, it's 2n to the 2 times n to the 4th. So the limit of that term is going to be 1 over 2, ratio of leading terms. Look at the next one. The degree of the numerator is cubic. N times n times n is n cubed, nothing higher. What's the leading term? 4 times 1 times 1 times 2, it's an 8. The denominator, 6n cubed, leading term is 6. So that term is going to go to 8/6. You guys see how I'm processing this? I don't have to write out. You can. My hand is tired. I don't want to write out anymore, but you can. Okay, so what about this next term? Can we just say it? It's going to be 6 over 2. The last term, the n's canceled, it's 4. So I'm going to keep this video short and let you determine how many, I don't know, sixths that is. I guess we could do it. It's 4/3 is the 8/6, and you've got 7 halves plus 4. I'll take you that far. You can finish it yourself and tell me how many sixths that is. All right, this is a long one, but it, I hope, is a very detailed illustration of how you can compute these things. Now it's your turn to practice it a lot.